Hey guys, welcome to Chem Squad Chemistry. Today we've got Mr. Mullins on the sticks. We are going to be covering Unit 4, which is our nomenclature unit. In this unit, you will be learning how to name 4 types of bonds, which are the organic bonds, the covalent bonds, the ionic bonds, and the acids. Now it's important that you keep these separate in your head because each set of bonds have their own specific rules that you have to follow. So it's important to keep them separate from one another so that we're not mixing them up. Today we're going to be focusing on organic naming, which is a type of covalent bond, but it's a very specific one that has its own sets of rules. So a couple of things you need to know about organic compounds is that they are made out of mainly 2 elements, carbon and hydrogen. Sometimes there's going to be some oxygen, but most of the time they're just going to be carbon and hydrogen. We refer to organic compounds as hydrocarbons because being made out of carbon and hydrogen. You may have seen some before, like this one. Glucose is an organic compound with a specific name. You've probably seen methane before, which we've drawn in the last unit. Even some of them that look like this, some of them get very large, where you have C10H22. All of these are organic compounds, and you notice that all of them are made out of predominantly carbon and hydrogen, hence the word hydrocarbon. So whenever you see something made out of carbon and hydrogen, you need to start thinking organic bonds, and we are going to be naming them. So there's 3 types of organic molecules that we can name, and we're going to memorize all 3. Our 3 types of organic bonds are known as the alkanes, the alkenes, and the alkynes. Again, say that with me: alkane, alkene, and alkyne. You notice that the endings are different. The endings actually teach us a lot about the organic molecule that we're going to be naming. Just a little brief tutorial on them. An alkane, whenever you see the ending ane, you should be thinking single bonds. Whenever you see the ending "ene," you should be thinking of a double bond. And you probably guessed it, with the alkyne, you're going to have a triple bond. So whenever you have a word that ends in "ane," "ene," or "ine," it is telling you the type of bond that exists. Also, there are some prefixes that we need to know. Hopefully you have seen some of these prefixes before, but just in case you haven't, meth means 1, eth means 2, prop means 3, but means 4, and from here on out you've probably seen them before, and they're also written in your book on pages 18 through 21. So what are we talking about when we're using these prefixes? We're going to be using the prefix and the suffix to create the name of our organic compound. Whenever we have meth, eth, prop, or but, what we're doing is we are counting the number of carbons. So if you were to look at an organic compound like CH4, you see that there's just 1 carbon. We would know that the prefix for that is meth. If we're looking at another one that says C5H10, we see that there are 5 carbons there, so we would be using the prefix pent. So if you don't already know these prefixes, you should memorize them. There is a little saying to help you remember the first 4, which is "me eat peanut butter." That's just a way that you can remember it if you'd like. Also, you know that if you do meth, you wind up with just 1 tooth. So yeah, there's that as well. So with that in mind, let's go ahead and practice with our alkanes. Remember that an alkane has single bonds, and we will be naming it. There's also a formula that goes along with this that you should memorize: H2N plus 2. This formula helps for us to calculate the number of hydrogens. We're going to know the carbon based off of the prefix, but in order to calculate the hydrogens, we're going to need to use this math formula, where N is the number of carbon. So it's simple: 2 times the number of carbon plus 2 will tell us how many hydrogens we want. So let's go ahead and look at something called propane. Hopefully you've heard of propane. If not, it's the stuff that we grill with. It goes on our gas grills outside. We use it to cook. If I were to ask you to tell me the formula for propane, you can start to break it down. We know that prop stands for 5. Oh, I'm sorry, that prop stands for 3, telling us the number of carbons is 3, so we can start to write our formula. The ane tells me that it's going to be all single bonds, so we're going to have 3 carbons all attached by single bonds. The next thing we need to figure out, since this is a hydrocarbon, is how many hydrogens are there. We're going to take this 3 and plug it into this formula up here, C3. 2 times 3 plus 2, so 2 times 3 is 6, plus 2 is 8. So here is my final formula, C3H8, that's propane. Sometimes you may be asked to draw it. You can see over here that we have our 3 carbons all attached with a single bond. The next thing that we're going to need to do is satisfy their octet rule. We can see the carbon on the left here has 1 bond total, so it needs a total of 8 valence electrons. We're going to satisfy that by sharing covalent hydrogens with it. We notice that this central carbon has 2 bonds, so we're going to satisfy the octet rule with 2 more hydrogens, and the far right carbon has 1 bond, so we need to satisfy it with 3. You notice that our drawing and our formula go hand in hand together. There are 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, just like we suspected. So with an alkane, we can use this formula in order to tell us how many hydrogens, or we can simply draw out the picture and satisfy the octet rule to see how many hydrogens there are. Let's go ahead and try another alkane. Let's look at naming one. Why don't we go with C10H22. So if I were to give you the formula and I ask you to draw it, or I ask you to tell me the name, in this case I just want the name, you would notice that there are 10 carbons, so we would use the word dec. And then we've got to think, oh, well, how do I know how many hydrogens there are? Remember our formula, H2N plus 2. We see that 10 times 2 plus 2 is 22. So that tells me the ending here would be decane, because all anes have that formula. So decane would be the correct answer for this one. Let's go ahead and practice drawing a few more, and we can write the formulas as we do that. So let's draw together butane, and then we will draw ethane. So butane, we see but, that tells me that there are 4 carbons, so let's go ahead and draw our 4 carbons. The ane tells me they are all attached with single bonds. Nextly, since butane is a hydrocarbon, we need to satisfy the octet rule. This first carbon has 1 bond, so it needs 3 more. We know that hydrogens are going to go there. The second carbon has 2 bonds, it needs 2 more to satisfy the octet rule, and so on and so forth. Satisfying the octet rule, no different than we did with Lewis structures. We now see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, so we know that it is C4H10. The other way that we could have gotten this formula, again, hopefully you're learning this, is that CnH2n plus 2 will help us to do that. So we take this 4, we plug it in. 2 times 4 is 8, plus 2 is 10. So we get the same formula. That's just a little easy way that you can be thinking about this. If it were up to me, you would memorize that formula, because it helps us later when we're trying to determine between an alkane or an alkene or an alkyne. It really helps to know that formula instead of having to draw out the super big picture. So let's move over here and go and talk about ethane. Let's write the formula first this time. Eth is telling us how many carbons. Me eat peanut butter, so eth is 2 carbons, so that's C2. And ane tells me it's a single bond. We know this is the formula for ane. So 2 times 2, just plugging it in right there for n plus 2, is a total of 6. Telling there's going to be 6 hydrogens. Let's go on and draw the picture. Single bonds, we know that because of ane over here. And we're going to satisfy the octet rule of both of these bonds, both of these carbons. And we have ethane. Let's do one more practice. Let's go with hexane. Hexane has 6 carbons because of hex. Ane tells us to use our formula 2n plus 2. So 6 times 2 is 12 plus 2 is 14. Going to connect them all single bonds because of anes, and we're going to satisfy the octet rule of all of them. So what we see here is a little shorthand. You notice I didn't write the hydrogens at the end. I'll write it for some of them. As you get better at this, you're going to notice that writing the hydrogens take a really long time, and it's okay to show shorthand sometimes. But on your test or on your quizzes, you probably want to go ahead and draw out all of your hydrogens, making sure the octet rule is satisfied. So now that we've talked about hexane and talked about alkanes, we need to talk about a little bit more terminology. So as we look at these hydrocarbons, some things can come up, mainly the word saturated. Saturated means to be full of, and in this case we're talking about a hydrocarbon which is full of hydrogens. You notice how each one of these carbons are holding as many hydrogens as they possibly can. They have single bonds connecting them to each other, and they are saturated. There's nowhere else on this entire molecule that we could put another hydrogen. This is a type of saturation. You probably heard the word saturated when talking about saturated versus unsaturated fats. This is actually what a fat would look like. It's a hydrocarbon chain. And because of the single bonds and all of the hydrogens, we consider it to be saturated. These are the fats that your body likes to break down first. They're real easy to break down because these single bonds aren't very strong, as in just a few minutes we're going to see double and triple bonds are much stronger. We'll talk about unsaturated here in just a few minutes. So now that we're comfortable with the alkanes, let's go ahead and talk about the alkenes. Remember that an alkene has a double bond just like that, and it has a formula of CnH2n. So because of the double bond, there's going to be less hydrogens than we saw in the last one, less hydrogens because of the double bond. Let's take a picture at it. Remember, the ending -ene will be shown. Let's go ahead and look at propene. Prop tells us that there are 3 carbons, C3. The ene tells us that we're going to be using this formula. So 2 times 3 is 6 right here. 2 times the 3 carbons is 6. So here's our formula. If we wanted to draw this out, we would have our 3 carbons. We would place a double bond somewhere. We'll learn where to put it. And then we start to satisfy with hydrogens. There should be 6. You notice that this first carbon is not going to be able to hold 3 hydrogens. It can only hold 2 because of the double bond. This next carbon has 1, 2, 3 bonds, so it's only going to be able to hold 1 hydrogen. This last one is going to be able to hold 3. So make sure you're satisfying your octet rule. You can see that there are some hydrogens missing, like there's none there, and there's none attached there. The double bond is keeping us from being able to have more hydrogens. And this brings us back to our vocab word that we just talked about, saturated. You can tell that this hydrocarbon here is not saturated. We could put more hydrogens here if it wasn't for that double bond. So what we would call this is unsaturated, otherwise not being full of hydrogens. Unsaturated things, like unsaturated fats, are harder to break down because the double bond is much stronger. Our body won't break that double bond unless it absolutely has to. So think of it as being stronger than a single bond. Let's go ahead and take a look at another alkene. Let's look at octene. Octene, oct tells us that there are 8 carbons, C8. Ene tells us there's going to be a double bond somewhere. Remember our formula. So 8 times 2 is 16 hydrogens. So as we go to draw this, we're going to run into a little issue. There's 8 carbons. How do I know where this double bond is located? Well, there's another step that we've not talked about yet. Typically, when you have a double or triple bond, it's going to be told to you where it's at, indicate it with a number. So the real name of the thing we're drawing is called 3-octene, where the 3 is telling us where the double bond is located, on the 3rd carbon. Now, there's always 2 options. You can count whichever way you would like. You can start at the left and number your carbons 1, 2, 3, 4, 5, 6, 7, 8, and you would put your double bond on the 3rd carbon because of this 3. Or you could have counted the other way, 1, 2, 3, 4, 5, 6, 7, 8, and your double bond would have gone over here instead of here, which is perfectly fine. Either way you want, just be consistent in the way you count. Some people like to count from left to right, and some people count from right to left. Whichever way you prefer to do it, just number your carbons and count that way. I'm going to go from right to left, so we have carbon 1, 2, 3. I'm going to put my double bond here. The rest of my bonds are just going to be single bonds. And then we need to satisfy our octet rule. So make sure you're careful here. You don't want to put too many hydrogens in any one location. See, this first one has 1 bond, so we got 3 there. Gonna need 2 here. You notice how this carbon has 1, 2, 3 bonds, so it's only gonna get 1. Same for that guy. 2 there, 2 there, 2 there, and 3 here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, just like we expected it to be. So here we have 3-octene telling me that the double bond is in the 3rd location. Now, if you would have counted from the other way, let me go ahead and show you what that looks like. We would have put it on the 1, 2, 3rd carbon here. These hydrogens would not have bonded. You can see it would have looked just a little bit different. But what you notice is that this is an exact mirror image of the last one that we put. So they're the exact same molecule, just flipped over the mirror, flipped over the axis. They look the exact same. Let's practice with another one. Let's go ahead and draw 2-pentene. We know that pent is telling us there are 5 carbons. The ene tells us to use our formula, this one. 5 times 2 is 10. When we go to draw this out, we know that our double bond is on the 2nd carbon. I'm going to count from the left this time. So we got it right here. And then the rest are single bonds, and we satisfy the octet rule. So you can see this is very repetitive. We would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So there it is, 2-pentene. Let's practice going the other way with the drawing giving the name. All right, let's go ahead and name this first one here on the left. We notice that there are 2 carbons. So what is the prefix for 2? Eth. We also notice that there is a double bond here. So what's the ending for double bonds? Ene. So this would be ethene. Now you need to denote where your double bond is located. We notice that it doesn't matter which side we count from. If we count from this side, that'll be our 1st carbon. If we count from this side, it'll be our 1st carbon. So we would just call it 1-ethene. Mirror images of each other. Over here for our next molecule, we're going to count, I drew it in shorthand without the hydrogens just to save some time, but we need to count our carbons. 1, 2, 3, 4, 5, 6. What's the prefix for 6? Hex. And we notice there's a double bond. What's the suffix that tells us there's a double bond? Ene. Next, we need to denote where our double bond is. You have to choose what side to count from. Be careful. You always count from the side closest to the double bond, which in this case is this side. So this would be my 1st carbon. So the correct answer is 1-hexane. You would never count from the far side. I would never count this way with my carbons, because then I would have 5-hexane, which is technically the exact same thing as 1-hexene. You always want to count from the side closest to the double bond. So the correct answer technically is 1-hexene. All right, so we should be getting comfortable with these. Let's go ahead and talk about our last type of organic compound, which is known as the alkynes. All right, so lastly, the alkyne. The alkynes have a triple bond somewhere. There is a formula that helps us to figure this one out as well. You're going to notice all these formulas look the same. So it's 2 less than 2 times. Let's start this time by naming a drawn molecule. So let's look at this one. Oh, sorry, didn't mean to draw that. You notice that this has far less hydrogens. So we could fit hydrogens in more locations, like here and here and here and here. So because it is not full of hydrogens, what word do we use to describe that? Unsaturated. So this is an unsaturated hydrocarbon because it is not full of hydrogens. So in this case, let's go ahead and name it. We have 3 carbons. What is the prefix for 3? Me eat peanut butter, so it would be prop. And we notice there's a triple bond. What's our ending for the triple bond? It's -ine. Lastly, we need to tell where our triple bond is, so we're going to name our carbons. Should we name them from left to right this way, or should we name them from right to left this way? The correct answer would be to name them from right to left, because we need to start at the side closest to the triple bond, which would be that carbon there. So in this case, it's on our first carbon, so we are going to refer to this as 1-propyne. All right, let's take a practice at drawing one on our own. Let's go with butane. Let's go with 2-butane. Oh, I left out the E in butane. So but tells us there are 4 carbons. Ine tells us that we can use the formula CnH2n-2. So 2 times 4 minus 2, that gives us 6. So H6. We draw our 4 carbons. The triple bond is located on the second carbon, so 1, 2, triple bond. We want to go ahead and fill out our single bonds and then satisfy our octet rule. So there's not going to be one there, there's not going to be any there. And we notice that this is again unsaturated because it's not full of hydrogen. There's only 6 when it could hold a lot more than 6. We see our triple bond is on our second carbon, so there's our correct answer. Now that you have learned to draw these, this is in your book on page 19, 20, and 21. There are some practice problems on page 22 where you will be drawing alkanes, alkenes, and alkynes. Again, on page 23, there is even more practice. But before we end the video, there's one other thing that we need to cover, and that is called a functional group. All right, so our last topic to get done with these naming of organic compounds is to talk about functional groups. A functional group is a molecule that attaches to a hydrocarbon that changes their properties. Now, there are thousands of functional groups that exist. We are not going to learn them all. There are some. I'll show you a couple. This would be considered to be an alcohol group. This is actually the one that we're going to learn. There's other groups that are called ethers, like this. You know, this is digging way deep into my organic knowledge, but this is called a ketone. I believe that this is called an aldehyde. You can see all of these different molecules will attach to a hydrocarbon and it changes their properties. But like I said, we're not going to be learning all of them. We are simply going to be learning about the alcohol group because it's something that you're already familiar with. Whenever you have a hydrocarbon that has an alcohol group on it, it's going to look and appear like a hydroxide, right? So if we had our hydrocarbon that looked like this, we notice this looks like our typical hydrocarbon, but instead of just having a hydrogen, we have this OH group. That OH group tells you that this is an alcohol. An alcohol. And whenever we have an alcohol, we must change the ending of our word to OL, all, just like in alcohol. So whenever you have a hydroxide group, we're going to change the ending to all. We notice here with this drawing that we have, there is 1 carbon. So let's go ahead and name this just like normal until we get to where we need to change something. We know that 1 carbon is meth. We see that there are all single bonds, so this would be methane. But because there is a OH on it, we need to change the ending, not methane. This would actually be methanol. Methanol. So this functional group of alcohol, the hydroxide, the hydroxyl group is what it's called, would actually change the way this hydrocarbon reacts. Let's practice with a couple other alcohols. Like what if we were to write butanol, 2-butanol. So the 2 is just like before. The 2 is telling us where something is. In this case, it's telling us where the alcohol group is. The but is telling us there are 4 carbons. The ane tells us they're all single bonds. And the 2 tells us where the alcohol group is. So let's number this way this time. The second carbon, we're going to have a hydroxide group there. And then we're just simply going to satisfy the octet rule with hydrogens. Just like this. So this would be 2-butanol. But is telling us the carbons, ane is telling us single bonds, all tells us an alcohol, and 2 tells us where it's located. So that's just a brief rundown of what an alcohol would look like. Let's draw one more, and then we will tell the name of the one that I'm drawing. So I'm going to draw you a picture, and you tell me the name of it. So here is our picture, and we want to pick the name. We notice that there are 3 carbons. What is the prefix for 3? It's prop. We notice they're all single bonds, so it's going to end in propane. But because there is an alcohol group, it's going to be propanol. Propanol. Now we need to tell where it's at, so let's number our carbons from the closest side. 1, 2, 3. This would be 1 propanol. 1 propanol. All right, guys, and I hope you enjoyed our little talk today. If you need any help, come see me or Miss Spivey. Also, there's practice with this in your book again. It's on page 21, 22, and 23. Have a good day.